Everyone, welcome to second Chandra lecture of the series by Professor Joe Silk. Yesterday you heard about the future of cosmology and how we should all start planning going to the moon. And today we are going to hear about nucleus star clusters and intermediate mass black hole. Joe, stage is yours.
So thank you again for the introduction. Well, today it's going to be a talk which is aimed at the astrophysicists and the potential astrophysicists in the audience, but I hope I won't lose too many of the rest of you as we go along. So I'm going to tell you about one of the interesting mysteries in astronomy these days, which is how the supermassive black holes that we observe to very high redshift and billions and some even 10 billion solar masses, how they're formed. It turns out they need seeds, smaller black holes are seeds, and I'll tell you about our attempts to locate these seeds and understand how they might aggregate into bigger black holes. Okay, so here is the distribution of the black holes that we've really measured very well so far. On the astrophysical side, that is the black holes that are formed from stars and merged together. You see a brief summary on the left, including the Nobel Prizes given for the discovery of the gravity waves from the mergers. And you make a black hole, of course, by accretion from a companion massive star, which tips the star over the edge, turns into a black hole, the more massive companion, and eventually those two will merge together. There'll be two black holes that merge together. Okay, so we've measured of order 100 black holes in this so far, in this mass range around 10 to 100 solar masses, and we're about to measure many more when the gravitational wave interrometers start turning on again very shortly with their new observing season. We estimate we'll have thousands within a couple of years. We also now have made immense progress with supermassive black holes. So these are black holes that typically might be 100 million solar masses, with some spread about that. We've imaged the black hole in M87. It comes in at 6 times 10 to the 9th solar masses. We measure its shadow, the shadow of its light. In the center of our galaxy, we study the orbits of stars in the central parsec, and we observe them speeding up as they approach the central black hole, and we measure the mass that way. And this is another experiment that's also been awarded a Nobel Prize. So it's taken very seriously now, the study of black holes. My guess is it won't be too long before the Event Horizon Telescope imaging may merit its reward in turn, but that's another story. But there is a mystery here, and that is that in between what I call intermediate black holes, that means 1,000 to a million, say, that mass range, we have very little evidence of them. They're very hard to detect because they're not really incredible accretors of gas and don't shine very brightly. You've got to look rather hard. And because they're sufficiently difficult to observe, we look for them in nearby galaxies. And most of the time, in fact, they're turned off. They go through cycles, duty cycles of activity. And it's really hard to see them when they're not producing any interesting, unusual types of light. I'll tell you a little about that in a moment too. Okay, so the issue is what on earth is going on for intermediate solar mass black holes. I should say that we need them to build the big ones. They're necessary ingredients in our cosmological astronomical mix of ingredients to make the big ones. We need to have 1,000 solar mass black holes or more as seeds. Okay, so this is a brief summary of how we measure masses of black holes in a wide variety of galaxies. And so this ranges from giant galaxies with lots of gas on that can feed the black hole, galaxies with little gas, and active galactic nuclei, which are the black holes essentially accreting gas and emitting directly. And the way we do this, the methodology is, well, the most elegant way is just by dynamics. Dynamics of the gas is complicated. We do that a lot, of course. But dynamics of the stars is beautifully simple. It's orbits of stars, and that will give you the central mass. We've worked that out to perfection for our own Milky Way and have done it with a number of other galaxies too, where we can resolve the stars, which is not necessarily that trivial. And then we can use more complicated things. I don't have time to go into them, which can measure the gravity potential and give us estimates of the central mass of the object. Okay, so that's something that's a well-followed science now, measuring black holes in quite distant galaxies. Okay, so this is a summary of what I'm going to be talking to you about. So these black holes of intermediate mass, one finds them in dwarf galaxies for the most part. And that's because there's a generic and universal scaling relation between the mass of a black hole and the mass of the galaxy, the stellar mass of the galaxy. And so the smaller galaxies have smaller black holes. And that's where we're finding them. And since there are a lot of them in the very nearby universe, we're beginning to build up a bigger sample of those. Okay, so what's really interesting, of course, is that the black hole can have a dramatic effect on the surrounding galaxy. And it does this, well, the black hole is in the center. It's the dense part of the object that collapses first. So you naturally would tend to get the black hole when you're first making the galaxy. And when that black hole forms and then starts accreting gas, it emits enormous amount of radiation and blows out a wind. And this affects the still condensing gas around it. And so this is what we call feedback. And the black hole has immense feedback on the galaxy and can turn a galaxy from being what would be a fairly bright object intrinsically, because it strips out much of its gas, it will become a dwarf galaxy. And so that's why there's this association of nearby dwarf galaxies with black holes. They can do a lot of damage on their surroundings, and some of the dwarfs typically will harbor these intermediate mass black holes, these smaller black holes. So because galaxy formation is complicated, once you add a black hole in the center and its outflows and various things like that, we often talk in cosmology about anomalous features of dwarf galaxies especially, which challenge the notion of dark matter. For example, some dwarf galaxies have cores. The theory predicts they shouldn't have cores. Many things like this. And what I will argue, I'll discuss this very briefly, but I want to emphasize now, is that because of the complexity, not just of forming stars, which then explode if they're massive, also having central black holes with all their feedback, there are no more anomalies in dwarf galaxies for which you need to invent some bizarre type of particle, such as fuzzy dark matter or something. There's no justification for this whatsoever at the moment, I would say. You can do it, it's fine, maybe they're there, maybe you can test these weird types of exotic particles, but we don't actually need them. They're not motivated, I would say, by astrophysics at this point in time. Just as alternative gravity is not motivated by astrophysics at this point in time. That's another story. Anyway, so what is going on in the centers of galaxies where we see these black holes? Well, a common feature to many galaxies is a nuclear star cluster. Now, this is a curious object. You've all seen pictures of globular star clusters. They're beautiful things. Some of the common objects that amateur astronomers look at, can study with telescopes. A nuclear star cluster is roughly the mass of a globular cluster and can be 100 or 1,000 times more massive. We observe these, but it's 100 times denser. The star density is enormous. We're talking about 10 to the 7th solar masses, equivalent 10 million stars inside a cubic parsec. That's 100 times larger than our own nuclear star cluster in the center of the Milky Way. And because these star clusters are so dense, they're great environments for colliding stars together, for making black holes, because they tend to sink into the middle anyway, and for merging the black holes and making the giant black holes. And that basically is the story of my talk. I'll try to give you some of the astrophysical details behind that speculation. Okay, so they're great environments for building up black holes by merging. Okay, okay, so let's move on. And let me now show you images of nuclear star clusters. So these are nearby dwarf galaxies. And when you look at them carefully, you see these bright, barely resolved points of light in the center. And those are dense nuclear star clusters. The ones I'm talking about that are much denser than the typical globular star clusters, of which there are several hundred floating around the Milky Way. That we have this very dense object in the middle, which may well have formed from the merging of a large number of globular star clusters. I'll come to that in a moment. But whatever, it's something that is certainly more exotic, more different from the standard globular star cluster, which we know very well from studies over many decades. Okay. So I first would like to go over with you a simple piece of theory which is behind the idea that the bigger the galaxy, the bigger the black hole is that is in the middle. And this is simply the notion of feedback. And it turns out that I'll show you by a very simple argument, back of the envelope argument really, that the bigger the galaxy, the black hole can grow to be more massive. There's more of a reservoir of material to feed it. But it reaches a limit when it's a certain fraction of the mass of the entire galaxy. And that is what explains what we observe, a great surprise. It was discovered some decades ago, the scaling relation between central black hole mass and the mass in stars of the galaxy, or more precisely, the random motions of the stars that define the potential well of the galaxy. And the way that scaling relation is explained is something like this. If I imagine the black hole is accreting gas from its surroundings, and the gas will heat up and it will be driven out actually just by the sheer accumulation of momentum. Now, we try hard to understand the interaction between what we see coming out of the middle, which is often in the form of a hugely energetic jet of plasma generated from the vicinity of the black hole and sweeping up the gas around it, all that's blown out. And so we consider two sort of limiting cases to try to understand what might be going on, whether the gas, as it sweeps up the stuff around it, this is typically a young galaxy with lots of gas, perhaps, we either conserve momentum or we conserve energy. And it's hard to tell which of those two is absolutely the relevant one, may depend on the circumstances, but one or the other, depending on the details of the plasma physics, is likely to approximate the truth. And we can test all of this with simulations, of course. I'm just giving you a very rough idea. Now, what is really intriguing is that if I have energy balance at the shock front where you drive out the gas, that means the gas becomes too hot to really cool down. And so it stays and it then pushes against the surrounding gas, this hot bubble, and stops the gas fragmenting into stars, maybe, but certainly it will eventually drive the gas out. It'll develop into wind and drive the gas out. So that's one self-limiting case. So it turns out that in the case where you have momentum feedback, that is, you couple by momentum, the gas can cool outside the central outflow, then it's a similar story. Momentum drives the gas out. And there's one really curious piece of physics that I find fascinating, that is, suppose, in fact, you conserve energy in this connection between the central gas and what's being driven out, then the momentum basically scales, you can see very inversely with the velocity, which means that as you put in, as you slow down the shock, you have more and more momentum transfer. It's like a runaway process. So this is a very intriguing property of shocks, how you can get, in fact, very strong boosting in momentum because you're conserving energy, basically. And so that probably does happen. The simulations suggest that does happen. Anyway, those are two examples of the physics we discuss, and we code up and do in hydro simulations ultimately. But I don't want to get into those. I just want to show you some simple arguments. But the main thing at the end of the day is that there is a connection, whichever limit you take, between the black hole mass and the random motions that define the potential well. These will be motions of stars, and that's the symbol sigma. And in these two limiting cases, you predict there's a scaling between the black hole mass and the random motions that define the potential well, which are defined by the stars, either a sigma to the fourth or sigma to the fifth. And that's a scaling you should have over many decades in mass of the central black hole. And the sigma is a proxy for the mass of the stars, of course, but it's more precise, according to simple theory, if it's the motions of the stars that define this. Okay, anyway, so you find that when you go through simulations, momentum boosting seems very important. And obviously, what this then tells you is something intriguing. If I have a small galaxy, it's going to have much more of a dramatic effect by that central black hole than a big galaxy, which is a deeper potential well. So that's the first remark. Small galaxies should certainly be damaged, and you might expect at the end of the day the small galaxies to be very faint galaxies, really low surface brightness. They've lost most of their raw material. That's exactly what we find, of course, in the nearby universe. That already tells you might be on the right track. And the other thing that tells you might be on the right track is that we measure the scaling relation between central black hole, measured in many different ways now, in a wide range of galaxies, and the random motions that define the potential well. Okay, so I'll come back to anomalies in galaxies in a moment, but let me just say parenthetically, the dwarf galaxies have long been a subject of conjecture in the theory community, especially in the particle physics community, actually to astrophysics, because they are always looking for some weak point in astronomy that needs an explanation that is beyond the realm of astrophysics to give. Okay, and for many years now, it's been thought that maybe the dark matter is such a nature that it cannot collapse into very sharp cusps, but in the center of the galaxy, but rests in a more diffuse core, and you can define various exotic types of dark matter particles. We call them warm dark matter, we call them fuzzy dark matter, to give you two examples, or self-interacting dark matter, a third. All of these are very popular among the astrophysics, particle astrophysics community, because they do lead you into new physics. And all I want to say now is that with this complex history of feedback from exploding stars, which I haven't even mentioned yet, but they do a lot of feedback on the gas. The first stars explode, push out the gas that will be making the next stars, and this central black hole, which is going to blast stuff out too. It's very hard to conclude that you're not strongly affecting the potential of the galaxy, especially the small ones, by the rapid dynamic motions going on in the center. And there are, in my opinion, no more anomalies to look for. But I'll give you a little more evidence in a moment of that. Okay, so here is this relation, which I think is one of the examples of how you can see astronomy in one picture, and you learn incredible amounts when you see this. Now, it doesn't answer any fundamental issues, but it gives you a sense, really, of the astrophysics that must be involved. So you have on the vertical axis the mass of the central black hole, the horizontal axis, the velocity dispersion of the stars, equivalent roughly to the mass in stars, but more precise when it's plotted this way. And there is this amazing correlation over 5 orders of magnitude or whatever in black hole mass. Okay, and so that has to be telling you something. And we think it's telling you something about the physics of the feedback of the black hole in blasting stuff out. And so the black hole limits the amount of gas that can eventually make stars. And that's what the simple back of the envelope theory on the previous slide tells you. So that's one interesting way that theorists, find something intriguing in the observations, and then one can build this into your galaxy simulation, including massive black holes, and try to develop models, improve models of galaxies. And this exactly is what is being done now in the latest simulations. You have to have your central black hole as the essential part, not just gas turning into stars that make a galaxy, but there's this highly non-thermal feedback as well, which can make life even more complicated because you can produce hydrogen particles, all sorts of things, which can also have empirical consequences. And so all of that is fascinating stuff, and it's all connected together. Okay, and so here's an example of a simulation by Dipanjan Mukherjee, And you can see this beautiful simulation in a dwarf galaxy. You have this central black hole ejecting a cocoon of relativistic material that runs into the surrounding interstellar medium, blooms out into this gigantic flower-like feature, and it's confined by the pressure, but it does squeeze, this overpressure does squeeze the disk of the galaxy, the gas in the disk, and induces it even to make even more stars. But it just self-limits the amount of stars you can make, this whole process. So it both creates stars and limits stars and stops star formation too by eventually driving the gas out. So that's the sort of thing that we think happens as learned from the simulations, again, to explain those simple back of the envelope calculations I was showing you. Okay, so the search for these intermediate mass black holes, it's really hard because they're not necessarily bright X-ray sources. A few are, very few are, we measure some that way. But there are other really fascinating techniques. One is you look for very unusual spectral lines. These are coronal lines, lines you see in the solar corona, really high excitation, iron, I don't know, 21 or something. Really, you see them in the X-rays or the extreme UV. And this tells you there's some dramatic energy input into the gas. And from the properties of these lines, their dispersion, you can infer the central mass too. So that's one method. Another one is studying outflows, again, from the gas emission in the centers of galaxies. And this shows you outflows versus the mass of the host galaxy. Here are the small galaxies, here are the big ones, very well observed in the big galaxies. And self-limiting the mass of the galaxy, the black holes become so important that you finally turn things off completely. And that's exactly what you see here. But on the smaller galaxies, likewise, as the potential well deepens more, you get stronger outflows too. And so it's seen on galaxies of all scales. And finally, microlensing, actually it's millilensing, because it's on milli-arcsecond scales of radio sources, is revealing interesting evidence for pairs of black holes in the center. Clearly, on the way to making your seed black hole, you better have mergers of smaller black holes. So we look for these as steps on the way to building up the big one. And these can be discovered now by really precise lensing, radio lensing on the milli-arcsecond scale of radio sources, radio nuclei. So that's interesting too. Okay, and then simulations are really leading the way in getting us closer to grips with the physics. This shows you a recent hydrodynamic simulation of the central regions of dwarf galaxies, a low mass one, a massive one. And the main thing that you can take away from this is that there are random motions and turbulence all over the place. So this is, there's nothing organized about these random motions. Things sort of dissipate and mix up very quickly as the jet from the center interacts, randomizes, runs into clouds, and then gets diverted and eventually mixes up. But all of this gives you pressure accumulation that then drives the outflow. These are pressure-driven outflows, as I explained, and they can be very powerful as they slow down and giving you very dramatic feedback. Okay, so that seems to, we call that momentum boosting of the outflows. That seems to happen. Okay, a few words on anomalies in the dwarf galaxies. So I mentioned this briefly. Now I'm going to show you a brief overview of all the major anomalies and why we don't think they matter anymore at the moment. So the first one is that when people began doing the simulations of cold dark matter and then got better at it and put the gas in, hydrodynamics, all that stuff, they found a vast number of small galaxies. So cold dark matter is notorious for having substructure. That we know, that we're sure of. It's cold, it fragments, it's unstable. Many, million solar mass substructures, or even smaller ones actually, and are almost certainly present in the dark halo. We're beginning to discover them, when they run into, we have galaxies merging with our central, the center of our galaxy, and they leave trails behind of stars. those trails are occasionally broken up by something invisible. We conjecture that's a clump of dark matter, for example. A million solar mass clump might do the job. So we have indirect evidence that piles up for this substructure. And the question is, why are there so many predicted in the early simulations, whereas we see very few? And so this contradiction is on the left here, where it says numbers. And here you see the number from the simulations, the number observed at that time. But it turns out that when you do a much more careful job of what I call counting the observed objects, when you put in the observational selection effects, which are very tricky because these are very faint galaxies, you find there's now perfect agreement that we don't get excess numbers of observed objects. There are lots there, certainly, but they're invisible, okay? But that's fine. We have no observational contradiction, which was what was claimed some years ago. Nothing to explain away. If we can prove there are no small dark ones, that's another story. We're very far from that at the moment. In fact, there's evidence for the dark things. Okay, so that's the number story. Then there's the question of the distribution of the galaxies we observe relative to the center of a galaxy. So again, the dark matter theory initially predicted that there should be more and more of these dark dwarfs with stars in shining as you move away from the center of the Milky Way. That came from the early simulations. But now that we do more careful simulations, we put in the disk of the Milky Way, we let these dwarf galaxies run through the disk on their orbits, they get tired and disrupted. And so you end up now changing completely the early predictions of a gradient to the numbers of dwarf galaxies. And you can see we now match the observations. That's this red line they do, and that's from depending on their orbital properties. You expect this sort of shell of dwarf galaxies around us, and that's more or less a fit to the data. So that's the sort of thing that we can do. And one more thing is the diversity problem. So, and we have a diversity problem too in galaxy formation theory, and that is we do see dwarf galaxies which have dense cores, and we see some which have less dense cores. So in fact, the observations are sort of all over the place. You can't really see that the old theory of pure cold dark matter, which predicted, spikes in the center, cusps, basically, you can't say that that's not right, that's for sure. But in fact, what we observe is a mixture of cusps and spikes. Now, cusps would be predicted by, for example, warm dark matter, because the particles basically get smoothed out over a certain scale from their intrinsic motions. So that might be a way to make a cusp. But in fact, with a dark matter model, it's very hard to have your cake and eat it. You can't have both cusps and cores. But with this mess of feedback that I mentioned in the early formation scenario for dwarf galaxies, you can have anything. And you can have some galaxies which retain their dark matter, others in which there's so much dynamical action in the central kiloparsec as the galaxy forms that you do form a cusp naturally in the dark matter. Okay, so it's all dynamics basically, and that's what does it for you. Okay, and so that we think is the reason for diversity. And then, so that's one thing with a nice social name, diversity. And the final one I'll mention, we call the too big to fail problem. Again, with other connotations too. But astronomers remark, cosmologists remark, that some of these dwarf galaxies predicted by the theory should be large enough and dense enough so they should be making stars. You can't stop them making stars. And we see, in fact, rather few of them. And so, again, where are the missing dwarf galaxies in this picture, the ones a little more massive than the smallest ones from the theory? Well, the answer is, again, almost certainly the feedback from this central black hole is complex enough to basically destroy any hope you have of making stars. We know this feedback works for big galaxies to some extent, and it's going to be much more dramatic for small ones. So that, I think, is the answer the simulators are finding now for the small galaxies. So it's goodbye to the problems, which is a nice thing, but it does open up another problem. And this is mostly what we're going to spend the rest of the lecture on, and that is the seeding problem. Given that we're finding black holes of billions of solar masses, 6 billion even near to us, MED7, and equally a very high redshift, redshift 6 or beyond, you have to have some seed to make them, because there simply isn't time in the universe to build them up by accretion, because you're limited by essentially the radiation generated when the accreting gas falls onto the black hole, which stops the infall of further material just by Thomson scattering. And that's called the Eddington limit of accretion. And so what do? Well, you're limited to basically, a few e-foldings of growth. That's what the simple theory says. And it's very hard to get around that. And given these few e-foldings of growth, if you start early in the universe, you don't have many e-foldings at that time to build things up very much. And so this is the sort of story that we are trying to do. We realize that if we want to have massive black holes at redshifts of order, 10, 15, which we're beginning to find indications of now, you have to have, it's just about impossible. If you want to make big galaxies over here, you need seeds that are enormous, okay? So what you do then is you say, well, let's assume the accretion is more effective. There's less of a problem with quenching it. And this is probably the most optimistic curves you can look at here. These are all observed massive black holes, okay, at rest between 5 and 10, 5 and 8 maybe. We're talking about 10 to the 9, 10 to the 10 solar masses. So to grow those, you need seeds in this mass range. You really do need 10,000 solar mass seeds at fairly high redshifts, redshift 10 to 20. So there seems to be no way around that unless you go for what is called super Eddington growth, and that is very, very hard to arrange. Okay, not impossible maybe, but hard to arrange. Okay, so what are these seeds? They should be there because this process is not super efficient at making the big black holes. There should be many seeds left over in the universe today of intermediate mass black holes, and probably they'd be in small galaxies. That's your best guess. Those should still have them. Those small galaxies merge together with time and make the big ones, but there are many left behind. It's just naturally an inefficient process. Okay, so nuclear star clusters are the place to go if you want to make these intermediate black holes in the early universe. So here is the dramatic point about the nuclear star cluster. They're incredibly dense. So right here, you see the globular star clusters. We know them, we love them, beautiful pictures of them. And they, typically have densities in these units of solar masses per cubic parsec of thousands. But when I get to the nuclear star clusters, they're 100 times denser. Okay, and they're also very compact. Okay, so parsec or less. Okay, so there are clusters in the centers of many galaxies. We see very few of them in the really big galaxies, not Milky Way, but 10 times the Milky Way, because we suspect that the really big black holes there will probably tirelessly disrupt them. But in almost all other galaxies, we find them, or when we look very hard, they're not easy to resolve. They're points of light, basically, in many galaxies, but they seem to be present. And we've discovered fairly recently in the past 2 or 3 years to harbor many of them intermediate mass black holes. Okay, so this considers the range of nuclear star clusters from 10 to the 5th to 10 to the 8th solar masses, and I plot it against the mass of the stars in the galaxy. So this is all data, can't really argue with it. And you can see that the nuclear star clusters that we're seeing go up to respectable masses, a few times 10 to the 8th solar masses. And they roughly track the mass of the galaxy as you go in the dwarf galaxy range. But then as you move up a bit in galaxy, it goes nonlinear, this connection between galaxy mass and nuclear star cluster mass. And I'll explain why that is in a moment. And we use different techniques to identify the masses of these nuclear star clusters, but this seems to be the pattern that we're having. And our interpretation is this, that in the limit of dwarf galaxies, lower mass ones, we have the linear part of this relation. It's just merging of globular star clusters, which sink into the middle. We only have 300 left in our galaxy. Once there may have been many more, and they form the nuclear star cluster, and they fall in with dynamical friction. They're fairly massive objects themselves. But when you get further back in time, and we see evidence for this, I'll show you in a moment, there's lots of gas around in the early universe, lots of accretion, and you get much more dramatic growth of these nuclear star clusters. That seems to be the story. Okay, so here is a cartoon for the scenarios I'm talking about. You can either have, to make these nuclear star clusters, you could imagine that you form some very dense cloud and you make stars in situ, or else you can have many smaller star clusters merging together to make these nuclear star clusters, and then they migrate into the center. So we don't really understand which of these two scenarios, but it shows you the range of options you have to consider. We try to piece things together as to how the nuclear star clusters might have formed. I can't really give you a totally common answer on that, where it's mergers of globular clusters or in situ star formation. Some combination of the two is likely, because when you look at higher redshift, you see lots of gas in these nuclear star clusters, as I'll show you next. Okay, so first of all, I repeat that they are massive, and that you see them up to a few times 10 to the 8 solar masses. The Milky Way doesn't have an exceptionally massive nuclear star cluster. Its one is about 10 to the 7th solar masses, but they go up to well beyond that. And as you go up in galaxy mass, there's this generic trend to have a more massive nuclear star cluster, as there was, remember, for a more massive black hole in the center too. So that, again, seems reasonably expected. You have more reservoir, more supply, more raw material to build these things up for more massive galaxies. It was this next slide, though, that is just fascinating now. Again, these are the newest observations, and we have various ways, I mentioned some of them, of detecting the black holes in the nuclear star clusters in the dwarf galaxies. And so look at the occupation fraction of nuclear star clusters in dwarf galaxies. It's remarkable. It's roughly 50%, and maybe getting high. The error bars are huge, okay, so let me not exaggerate too much, but of order 50% you can take away from this. And that's not surprising at all, because you only find the black holes because they're doing something. Gas is forming and giving some signal, right? If you didn't have that signal, they'd be dead, that they wouldn't be emitting anything. And so we know that whatever we see is a lower limit on the total number out there, okay? So having these intermediate black holes everywhere in all is quite possible, and maybe even likely, given our inefficiency in understanding, in keeping them alive and detectable. So that seems to be one interesting part of the story. And then there is this connection between black holes and nuclear star clusters. First, let me say that in globular clusters, we do not have massive black holes, okay? We've looked very hard in globular clusters. There are limits of 1,000 solar masses. There are one or two examples which people discuss endlessly of whether there is 1,000 solar mass black hole in the globular cluster. But by and large, the answer is no. And the red points on this graph are the globular star clusters in the Milky Way. Black hole mass, nuclear star cluster mass. So forget it. These are basically all upper limits. There might be an example or two there. But we're talking 1,000 solar masses, which is, the very lower bound of what I need for my seed black holes. But as you move up in mass, you're finding now increasing numbers of candidates, okay, which go all the way up in black hole mass, up to the biggest ones, actually, but these are slightly bigger galaxies. I mean, this is amazing. Look at this, a black hole of 10 to the 9 solar masses in a galaxy, which isn't much more. So one is finding extreme objects, but ignoring the extreme objects. Let's just take the mean. You can see that there are, black hole masses, maybe 10% of the mass of the nuclear star cluster, all the way back to galaxies that span the dwarf range, okay, of galaxies. So the black holes, and if you now allow for the ones that we don't see, are most likely to be there. Okay. So one more intriguing prediction about this whole theory, you're merging together small things to make big things. You're merging together dwarf galaxies, nuclear star clusters, the central black holes with other ones. And there are inevitably going to be dynamical kicks, especially of these black holes. As they merge together, the merger product will get a dynamical kick because the merging won't be spherically symmetric. There'll be some momentum ejected. It's very likely that part of this story is there are wandering black holes. Okay, wandering intermediate black holes, because we know there are lots of them, because they're the building blocks of the big ones. Okay, so evidence is a little sparse on this right now, but so these are examples. Some of these may be foreground background effects, not real, but in this recent survey, the red dots represent radio sources, which are the AGN, and they're inevitably, well, these examples that were chosen by Amy Reines, they're off center by hundreds of parsecs. And you can calculate why they would go off center. It could be the kicks from mergers. It could be dark matter substructures that kick them out. The jury is out on exactly what's causing the kicks. If there even are kicks, it has to be justified completely, but it does seem likely theoretically. There are just too many ways to kick these things out, but there are so many that we'll have no problem making the big ones eventually at the end of the day. Okay, so finally, a little bit of theory. Okay, so this is some work that I've been worked on. This is my student, Kostas Kritos, who's at Johns Hopkins. And so what he's been doing is studying the mergers of black holes in nuclear star clusters. And so the black holes were initially made from stars, 10 solar mass, 100 solar mass black holes, and they merge with, and they sink to the middle, they merge with other black holes, and eventually you build up to bigger and big black holes. Along the way, you do kick the smaller black holes out, some of them, from these mergers. So you end up typically in the most massive, the most compact nuclear star clusters with one big black hole and lots of very small ones left over from the beginning, gravitationally bound in the nuclear star cluster. So this sort of shows you 3 examples of Kostas' simulations for nuclear star clusters that range between 100 million and 1 million solar masses. And this represents the properties of this massive one. These are the individual black holes, and this is the massive black hole. So this cluster have a black hole in the center, in this case of 1 million or a few million solar masses, and lots of smaller ones. Okay, and similarly for the other colors there. So the idea is that, well, these black holes do merge together and they will give you gravitational wave signals. So that's the way you can actually test this theory. That's the idea. And this shows you, first of all, again, for that model I highlighted just now, a close-up, and you can see the mass of the primary black hole. There's one massive black hole in this cluster and lots of smaller ones. And eventually the small ones will merge with the big one, some of them, and give you gravity wave signals. And in this theory of nuclear star clusters, of course, you merge some, you destroy some. As they lose lots of mass, they expand some. And this is just a comparison of the models with actual data on nuclear star clusters. And it's not, there's lots of overlap of points. I won't go into that. It's not a terrible comparison. But what's really interesting are the predictions for the future generations of gravity wave telescopes. So this shows you then the sensitivities of LISA, that's our space interferometer measuring low frequency gravity waves. That's its sensitivity limit in terms of frequency. You have LIGO, Virgo over here in 3 or 4 years' time, their projected sensitivity limits. And these are the future, the 3rd generation detectors, the Einstein telescope, the European one, the Cosmic Explorer, the American telescope. Roughly speaking, we're looking at the end of the 2030s for these. They're 40-kilometer baselines and cryogenic and buried compared to the 4-kilometer baseline of LIGO Virgo. And these then are the merger rates predicted by the simulations. First onto the massive black hole, that gives you a lower frequency, this is a larger, and then between the smaller black holes in the models that I showed you. So there are lots and lots of events to be explored that will peak above the sensitivity limits for these nuclear star clusters. One can perhaps see the action going on. One will see these events, from one spot in the sky, the nuclear star cluster, and of course many others going on at roughly the same time too. Okay, so this is almost the last slide I'll show you. I just wanted to come back to the question of how do you form nuclear star clusters? Well, nobody knows, but here's a really intriguing observation of a lensed arc from the James Webb telescope published recently. And you can see these incredibly bright and compact star clusters, okay? Now, no one knows if these are small galaxies or nuclear star clusters, but I think these are candidates for the formation at high redshift. And then their masses are roughly right. These could be forming nuclear star clusters. They're things that should form most likely when the galaxy forms. So maybe we're beginning to have the ability to see small things via magnification in redshifts as far back as 6. So these are the masses and the sizes to be possible forming nuclear star clusters. It's maybe not, maybe there's something else, but but it's a first glimpse from the early release data. Okay, so let me now turn to a summary of my talk. I have tried to argue that the problems we've had up till now by looking at the dark matter properties in dwarf galaxies may not be problems. I don't think they justify the somewhat exotic particle physics that has been discussed over a number of years now, over decades now, as giving you a solution to the problems of astronomy. It's not as though we're repeating Einstein's adventure with the advance of the baryon of Mercury. Very far from that, with observations that have not stood centuries of test, but rather are, I would say, are just simply not robust relative to the unknown physics that's around. And that can be done thanks to appealing to these black holes into the dwarf galaxies and also exploding stars. Didn't talk about that much, but every time you make any number of stars, you'll make some really massive stars, have violent explosions, supernovae, and that will stir up the gas. And again, the dynamics of that stirring up will affect the dark matter distribution in a complicated way. So it's very, very hard to say much of any fundamental nature about the dynamics in dwarf galaxies because there's been so much processing, basically. Then I've argued that these intermediate mass black holes form early in nuclear star clusters. They have a history of merging and gas accretion to help them grow bigger, and they will leave signals behind to see via gravity waves. And this may be the explanation of making the seeds of the supermassive black holes. They have a large population of seeds at higher redshift, and they, as the structure basically merges together and builds up, are an ideal candidate for explaining supermassive black holes. So that's the end of my story. Thank you.
For this wonderful talk, especially this back of the envelope argument about M sigma relation. It was wonderful to see. Do we have questions?
So these exotic scenarios where you bring in particle physics to explain cores and cusps, and now you can explain it using astrophysics. So whether it's astrophysics or particle physics, we don't know. Both will change our cusp to a core. Question is, how do you differentiate between these two?
My only point was really that it's fine to discuss the particle physics, but they shouldn't be used as motivation, saying there's this particle out there, let me explore it. And as to distinguishing cusps from cores, one can, I think our best hope is to use stellar dynamics to basically infer the matter distribution of dark matter around, ideally, the central black hole, because that is a beacon. And the dark matter collapses around it, and whether it's a cusp or a core, that distribution will have a signature of how it fell in there and where it came from. So that's our best bet, using classical stellar astronomy, except that you need to use ultra sophisticated cameras now, because you need this exquisite resolution to study individual stars. We've done this beautifully for the center of the Milky Way. We still can't say with the gravity experiment, which measures the orbits of these S stars that measure the mass of the central black hole, we still can't say how much dark matter there is in there, in the very central parsec. The experiment currently sets a limit of thousands of solar masses, and we can't yet tell if it's distributed like a cusp or a core. But it's amazing that we can say already at the moment from dynamics, the dynamics that effectively won the Nobel Prize by Gensel and Ghez, that there is possibly something extra in there. And so that's the sort of direction I think we need to go in to refine these experiments, both in our galaxy and in nearby galaxies, to see if there is some extra ingredient that might be the quote unquote dark matter and be either in a cusp or a core format. That'll be my best.
Just to follow up, suppose we differentiate it and know that it's a cusp or it's a core. Suppose we say it's a core. Now it can be a core due to feedback over a billion years, or it can be a core due to your particle physics properties. How would you differentiate between these two? Not a core.
With very great difficulty. Yeah. That'd be very hard. Yeah. Yeah. I mean, it's not crazy because some of these particle physics scenarios do have intriguing, predictions. For example, fuzzy dark matter has a giant soliton in the center, and that's an oscillating gravity field, and that might have some unique signature on the stars. Things like that. We have to model this all much better, probably. So I don't think it's ruled out, but right now there's nothing terribly obvious.
More questions?
So you said that nuclear star cluster could be the place where you can form intermediate black holes, but we don't understand how nuclear star clusters form. So does it feel like you're replacing a question with another question that you don't understand? Like it feels like kicking the can down the road sort of problem?
Yes, I agree with you. That is an issue, and I mean, that's the way we tend to proceed in astronomy. We solve one problem, and that poses another question. And often we can push this back a bit in time, but right now we don't know how it all began. The nuclear star cluster, certainly, probably for a lot more things too.
But then the argument that we should look for nuclear star clusters, like how strong is that of an argument? Because how often do we find nuclear star clusters in the first place for dwarf galaxies? Right?
Very often, and the observations suggest it could be, they're still very incomplete. These things are not always easy to detect. And so the view is 50% of dwarfs, I think, could have them of that order. And the uncertainties are huge. We don't know.
Yeah. So one thing I was confused about, so some of your nuclear star clusters go up to around 10 to the 8, 10 to the 9 solar masses. So how do we actually differentiate between these nuclear star clusters or, dwarf galaxies themselves? Is it through the mass to light ratio? What is it that we try to do?
It's just that the nuclear star cluster is very compact and incredibly dense.
Okay.
It's less than a parsec
I
across.
see. Whereas the
Dwarf
galaxy would be much
is
more
really
diffuse.
diffuse and hundreds of parsecs. So the observation is very easy to tell them.
And the other thing is that you mentioned that we don't think that there are these massive black holes in globular clusters. That's an observational
That's an observational fact. That's right.
Okay.
Yes.
I see.
And the data is still, there's a mass you can rule out of order 1,000 solar masses, but that's where our constraints stop, basically. But nothing bigger is seen in any globular cluster.
But in principle, could we form IMBHs given the globular cluster stellar profiles, or do we need
our
something as
ignorance
cusky
of the formation history is such that we don't know. I mean, they
Okay.
could certainly have formed when the globular cluster formed, or from mergers of the remnants of massive stars, etc. So uncertain.
Thanks.
So actually, following up on Sushmita's question, in the low mass regime, I mean, I saw there were there were nuclear star clusters as small as 10 to the 5 solar masses, but we also know that we have globular clusters as big as 10 to the 5 solar masses. So in the low mass regime, how do you differentiate between globular clusters and nuclear star clusters?
Well, only in the nuclear star cluster is at the center of a small galaxy, or any galaxy.
Okay.
The globulars,
Could be anywhere. Okay, I see. Okay.
So do you know anything about the status of the strong lensing searches for these dark subhalos?
Let's see. All I can say is from memory, and that people have been looking at multiple images of quasars and looking for image asymmetries, and that sets some limit on the component of the lens that might be a dark substructure of order tens of millions of solar masses, as I understand it. So they can set up limits, and maybe even infer there are such things, although I'm not even sure how reliable that statement is.
Questions in the room?
So usually we say that the globular clusters are like a very old, like they carry a very massive and old stars. So what about the nuclear star clusters, like the age, the typical age that we can assign?
Okay, so globular clusters generally contain just old stars. We certainly don't see any which are forming stars. Again, there is a range of ages. There's very old and not quite so old, two populations of globular clusters. But for nuclear star clusters, the story is different. The ones we see nearby tend to be old, but the ones we see far away, many of them have gas and emission lines and even young stars. So they are forming stars. So it's a mixture, and they are nuclear star clusters too. So we may be seeing them early on in formation even. And they tend to be more massive than the ones nearby. So it's all, a little uncertain as to, when any object formed, and what its counterpart to
There should be a lower limit, like after this, there should be a lower limit that we can assign.
Lower limit on?
The formation, the time of formation.
Yeah, in general, the universe is pretty old around us today. We can't actually point to some nearby object and say, there's an explosion of forming stars there that's forming a nuclear star cluster. Maybe someday we can do that with better data. I don't know. I don't know of that argument being made, but so it could happen today. There's no reason that forbids that.
Any more questions? Okay, maybe I'll ask one last quick question. So you elaborated a lot about M sigma relation, that's black hole mass, and the velocity dispersion of the stellar mass relation. There's similarly in galaxy clustering literature, there's a halo mass and stellar mass relation. And that means when you look at brighter galaxy, you'll find that the overall clustering amplitude of these galaxies is higher compared to fainter galaxies. And so people have tried quite a bit, at least around Redshift 1 surveys, where they want to see if you choose black hole mass of different region, higher or lower black hole mass, that should affect galaxy clustering or quasar clustering. But that hasn't been found. I don't know if that sort of poses a problem to this M sigma relation, which doesn't seem to exist at higher redshift in a naive way if I extrapolate in this way.
Yeah, I'm not sure about that. I mean, you're saying that there should be, massive galaxies have massive black holes, and they are more clustered than perhaps. I'm not quite sure what you'll be looking for that you think might be an issue. You mean the lower mass black holes should be clustered, for example? Or?
Mass black holes should have lower clustering amplitude compared to high mass black holes.
Yes.
SDSS people have looked for this.
I don't know of anyone that's interesting. I don't know of anyone that's really looked for the clustering amplitude as a function of mass for the black hole. Interesting point.
It's like clustering is looked at as a function of the AGN luminosity. There you don't see anything.
Yeah.
But for masses of black holes, I don't think there are like such a huge.
So same thing people have tried with the masses by
AGN luminosity, you don't see much, but that could be just like the accretion rate differences,
Yeah, there's a lot of
which is causing the luminosity, right? Yeah, which affects.
Black hole mass estimates are through these complicated physics in terms of
Sure, yeah.
emission regions.
Mhm.